So this is a very simple introduction to Riemann surfaces. I'm not going to do everything on the subject, it's too vast. I'm just going to give a very introductory lecture. The idea is the following. In physics, you very often encounter such equation, p of xy equals 0, where this is a polynomial of two variables. And there are two kinds of things you want to do. One thing is you want to study the set of solutions of this equation. So basically, this gives what if you solve in terms of y, it gives y as a function of x. Okay. As a function of x, and as a function of x, in fact, it is usually multi-valued because there are several solutions, and those solutions make several, so basically it's a multi-valued function, it's several copies of functions, and it's very good structure where you can define it really to be analytic. So a very simple example is the equation y squared equals x, so which will lead to y equals plus or minus square root of x. You know that the function square root of x is not analytic in the complex plane. To make it analytic, you have somehow to take two copies of a complex plane and glue them in a certain way. And when you do that, square root of x can be considered analytic, but in something which is not the complex plane, which is a Riemann surface. And that's somehow why the reason why Riemann introduced Riemann surfaces is to make such functions analytic in a larger space than the complex plane. Another thing you want to do very often is to be able to compute integrals. So imagine you want to compute something like integral over dx. Any rational function on some contour, you want where r is, let me replace this by y of x, where y of x is solution to that equation, where y of x, p of x, y of x equals 0. So we want to solve that. So a very simple example is, imagine you want to compute, for instance, the integral of dx, square root of x squared minus 4. Let me do that. Dx, x to the k. Imagine you want to compute such an integral. Here this will be simple because there is a simple change of variable. You write x equals z plus 1 over z. Okay, then this integral becomes integral of z plus 1 over z to the k. Dx is 1 minus 1 over z squared. Let me write it z minus 1 over z dz over z, and divided by on square root of x squared minus 4 is just z minus 1 over z. Okay, the denominator cancels the term, so you are left with just integrating a rational function. This is quite easy. So basically what you get is that this integral is the integral of z plus 1 over z to the power k dz over z. And so this is this is the integral of the differential of z to the k, so 1 over k z to the k minus z to minus k. If k is different from 0, and this is integral of d of log z if k equals 0. Okay. So what I'm just saying is that when you have an integral involving square roots or involving algebraic functions, so basically the idea is you want to be able to compute integrals involving algebraic functions. So this is an example. In that case, this is quite simple because there exists a good change of variable that makes it just integrals of rational functions, which you can do. And you see that the result is either the integral of the derivative of a rational function, or it can involve logs. You have several possibilities. So the idea of what we are going to do now, what I'm going to talk about, what people are interested in, is when you want to compute the integral of some rational function of some algebraic functions, involving algebraic functions. So you want to integrate an algebraic function. We want somehow to classify the result. So some of them will be rational, some of them will involve logs, and so on. Can we classify the result? Can we compute all those integrals? So that's more or less one of the goals of algebraic geometry. So this was just the introduction, and so let me now start to introduce
Bertrand,
the formalism
question. You were a bit vague about contours in this example.
Well, it does not really matter, because when you integrate a total derivative, it's just, so the integral is just the value of a function that's there taken at the boundary of a contour. So it does not really matter what it is. Well, what I just want to say is that there is a method to be able to compute.
On the relation with Riemann surfaces of this second point?
Well, you see that this involves an algebraic function. And here the idea is that through a good change of variable, you can make it rational. So it's called the uniformization. You can uniformize your algebraic function to make it somehow in a more standard way. And in that standard way, the computation will be easier. That's the general idea. So, but here it was a simple case because it was a genus 0 Riemann surface. For more general, more complicated cases, we will see. So, let me start by defining Riemann surfaces and first define manifolds. So this is the first chapter. Manifolds, surfaces, cards, and all that. And the first thing will be really the definition. So, manifolds. So I remind you the definition of a manifold. A manifold is a topological space well, in fact, let me say separated. Separated means that distinct points have distinct neighborhoods. Distinct points have distinct neighborhoods, so you can always find, so if you give yourself two distinct points, you can always find two neighborhoods that do not intersect. Separated, and there is another thing, is that it's called second countable. Space. So second countable means that you can generate all the open sets by a countable. I mean, you can generate the topology by a countable set of open sets. So there is a countable basis of open sets. It's not always taken in the definition of Riemann surfaces. You can or you can define manifolds without that, but it's we are more regular with that. And that is locally Euclidean. Which means that every point has a neighborhood homeomorphic to an open set of R to the n. Okay. So it means you have your big object M. Every point admits a neighborhood that is set to some Rn. And an homeomorphism means that it's bijective. The inverse, it's bijective and continuous. And the inverse is continuous. In fact, we will consider also later, I will talk about more general, some special sets of homeomorphisms that will be in addition C infinity or analytic or something like that. I will do that later. What we call a card, an atlas. So an atlas so a card is a pair where V is a neighborhood. So it's an open set included in your manifold. And phi V is the homeomorphism phi V that goes from V to U. So let me call U the image in Rn. The homeomorphism. And phi V is called the coordinate. In the card. So an atlas is a set. An atlas set of cards that cover M. And such that if you have two neighborhoods that intersect, it's a countable sets of cards, so let's call them Vi phi I, such that if Vi is different from 0, then what's then the map psi ij that goes from Vi inter Vj to that goes from that goes from the phi I of Vi inter Vj, so which is a subset of Ui, into phi j of Vi inter Vj, which is a subset of Uj, which to a point P associates phi j, phi I minus 1, So basically psi ij equals that. So it's an homeomorphism of Euclidean spaces. So is an homeo of Rn. So basically, if I have two cards that intersect, so this one is ui, this one is uj, this one was vi and vj. On the intersection here is sent to a domain there and a domain there. And the map psi is the map that goes from there to there, psi ij. And you want it to be a homomorphism.
But if psi I and psi j are homomorphism, then psi ij is also, isn't it?
Yes, but now you want to say that it's an homomorphism of Euclidean spaces, and you will require something more. So then I will define. So the definition is that M is a smooth manifold if psi ij is a C infinity homeomorphism, and M, and if the dimension n equals 2 and you identify R square with C, and M will be a Riemann surface if psi ij is analytic.
And I have a question on your definition of the manifold. So for the two lines that intersect, that's not a manifold, right?
Yes.
Because the intersection point
Yes.
is
Not
singular.
yes, the neighborhood of an intersection point is not locally Euclidean disk or something like that. So this is just the abstract definition of a manifold or a surface. So a surface sorry, I just need to say something more. Two atlases are equivalent if their union is an atlas. Okay. So now let me say a few more things. So if n equals 2, this is a surface. Okay. So I already said, so if the transition maps are C infinity, this is called a smooth manifold. If the transition maps are analytic, this is called a Riemann surface. And the surface is orientable. Sorry. The manifold N is orientable if all Jacobians d psi ij of x. So remember, this is a point in Rn. So this is x1, xn, And this is a point in our n, so m, which is 1 to n, over d xi, sorry, dx k. Well, let me write it this way. So for every transition map psi ij, you take the determinant over KL is positive. So if all transition maps have positive Jacobians, the manifold is said orientable. And there is an easy theorem, which is that for Riemann surface is always orientable. And this is because, so here you have a two-dimensional, so you have a 2x2 determinant, and using the Cauchy-Riemann identity, you realize that this determinant is just the modulus square of the derivative of psi. So in that case, this will be this determinant will be psi ij of z square, so which is always positive. I'll let you do this computation. So every Riemann surface is orientable. Yes, another thing, compact. So let me take as definition of compact. So if there exists a finite atlas whose cards UI are compact. Well, are bonded, I should say, by a ball in Rn. Okay. I need to write all these definitions that are quite abstract because we will want to define a Riemann surface from an algebraic equation and check that it is indeed a Riemann surface. And there will be important subtleties, especially regarding compacity.
So this is definition of compact Riemann surface. Or
This is
compact
not
manifold.
truly this is not the true definition, but it's a theorem that for Riemann surfaces this is more or less equivalent. And it implies that every sequence of points on M has an adherence value so basically in every sequence there is a subsequence that is convergent. And yes, and it's very convenient. Let me just define a manifold from an atlas. So here, somehow in my definition, I assume that I already have my topological space M, and I equip it with some homeomorphisms to Rn that are compatible through transition maps and so on. So basically, I already have the object M beforehand. Now there is another way to define the manifold. It's you just have the subsets of Rn. So basically, in my picture before, I had this, my M, and I had my open sets Vi, Vj. This one goes to Ui, and this one goes to uj. And on the intersection, and I had some thing on the intersection, psi ij. That was a homomorphism of Rn. Now imagine that you give yourself only a set of open sets of Rn with their transition maps, the psi ij's, and you don't have m beforehand, you don't have the vi's, you don't have the phi i's, you just have the right side. So you just have a collection of open sets of Rn and transition maps. Can you define a manifold? This is what I will call an abstract atlas. So this is a collection. So this is I enumerable set. So this will be the set of indices of the UIs. Open set of Rn for all I. I will also define some Uij. So basically my Uij will be that region, and here you will see I will have Uji. Uij included in Ui, and maps psi ij that goes from Uij to Uji, which is a homomorphism. So depending on the kind of manifold I want to define, I can choose it continuous, C infinity, analytic, and so on. Okay? What I mean by homomorphism, it's taken in the good class, so either C infinity or analytic. So for our case, it will be analytic for Riemann surfaces. But that's not enough. That's not enough. I want to require something else. I want to require that psi ij, psi ji must be identity. And I want to require something more. I want to require that psi ij, sorry, oops, sorry, psi ik psi jk equals psi ik psi ji. Well, on the corresponding well, whenever you are on the desired ensembles of definition, and I want to require something else, I will define Uii equals Ui. So what this means is that now if you have three intersecting neighborhoods, Vi, Vj, Vk, okay, you have now a common region to all the three here, and you want to make sure that this is compatible. So here you have Uk, so here you have one smaller subspace, and you want to make sure that the transition map to go from there to there is the same as the transition map going from there to there, composed by the transition map from there to there.
Sorry, can you give example of non-equivalent atlases?
well, so if you take C infinity or, for instance, analytic, so an equivalent class of atlases is called, for instance, for Riemann surfaces, an equivalent class of atlases is called complex structure. So which means, so I will give some examples later, but if you consider the torus, you can equip the torus with different complex structures that are not equivalent. But for instance, for the Riemann sphere, in fact, there is only one, the equivalence class consists of only one complex structure for if you have a simply connected Riemann surface, simply connected surface, there is only one complex structure on it. It's unique. So we'll come back to that later. So what I want to insist on is that, so you want to make sure that when you compose the transition maps, it's equivalent to doing that. So it commutes. This is the condition for this to be well defined. So if you have an abstract atlas, there is a very easy way to define a manifold. There is an easy way to define a manifold, which is from an abstract atlas. So basically, you want to define. So you want to take several copies of Rn, as many as the number of UIs you have, cross I. So basically, your manifold will be defined as copies of Rn, so a subspace of that. So we are going to take a subset of that. So we are going to take the space of pairs xi such that, belonging to that, such that x belongs to ui. So it's a subset of Rn cross I. Okay, but that's not enough. We shall quotient it by an equivalence relation. And the equivalence relation is simply that xi is equivalent to xj, to x prime j, if, and only if, xi equivalent to x prime j, if x belongs to uij, x prime belongs to uji, and psi ij of x equals x prime. And this is an equivalence relation thanks to those two conditions. The second condition was psi ik was psi jk was psi ik psi ji. So thanks to these two conditions, this is a well-defined equivalence relation. So this is a well-defined quotient, and so M, defined this way, is a manifold. Okay. So which just means that if you have an atlas, you can define a manifold in a unique way. So now let me take examples of Riemann surfaces. So my first example will be the Riemann sphere. And I will define it in several different ways, illustrating those, all those concepts. So the first definition will be consider the Euclidean sphere in R3. defined. So it's the set of points x, y, z, such that x squared plus y squared plus z squared equals 1. Okay. So it's something like that in R3. And I will define two cards on it. Two cards. So I will define the first card V1. That will be so V1 will be the space, will be the set of x, y, z, such that x squared plus y squared plus z squared equals 1, and z larger than -3/5. And phi 1 of x, y, z will be x plus I y over 1 plus z. Okay. And it maps so it's called the stereographic projection. You take the south pole and you shall project on the Euclidean plane which goes through the center here, and which we shall identify with C. And basically to every point of your, so V1 is everything that is above this height. V1 is everything about that height, and every point on your sphere belonging to V1, you make the straight line going to the south pole, and it intersects the plane R2 somewhere. So on this maps, so phi 1 maps V1 into the disk of radius 2. I'll let you check, and this is why I choose this -3/5. It's because it gives the radius 2, but I could have chosen something else. Okay. The other card is obtained by choosing the north pole. So V2 will be the same thing with Z smaller than 3/5. And phi 2 of x, y, z will be x minus y I over 1 minus z. Let me check. Yes. And it maps V2 into, so this is what I will call U1, and again D02, which is U2. So both are mapped to the disk of radius 2. And the transition map psi 1, 2 of z is just 1 over z, which is analytic. So basically it sends the disk of radius 2, so it sends U1 to U2. And what it sends, in fact, it's the annulus into the annulus. So which was the intersection of V1, so this annulus is the intersection of V1 and V2. So it's the, on the sphere, this is the region, the annulus is there. Okay.
Sorry. In your previous definition of the manifold, you said that the transition map should be a homomorphism of R of N, but here it's the topology.
Okay, it's an I said that for Riemann surfaces, I consider R2, and I identify R2 with a complex plane, and I require my homeomorphisms to be analytic. What I call an homeomorphism is analytic function for R2 identified with C. A holomorphic function. So that will. So okay, maybe it was not clear. For Riemann surfaces, you insist that the transition maps must be analytic.
No. I mean, you first define give the definition of the manifold, and you write on the blackboard that phi ij is a diffeomorphism of the Euclidean space R.
Yeah.
But here the topology of the two intersections is actually the S1 product R1, not R2.
S1 product R1. Well, okay. I want to identify the disk in U1 so it's a subspace of R2, but that I identified in fact with C. Basically, I identify R2 with C.
Bertrand, tu as deux Z. Il y a le Z de R cube et le Z qui est X plus Y.
Okay, I see. This Z is not that Z. In my notes, this is a lowercase z. This is, okay. Okay, I should call them I should call them x1, x2, x3. Okay. And here it's x3. Maybe does this so this is what we shall call Z. Now it's a complex value. Something which is complex valued. It belongs to C. Okay. Maybe I was not clear enough, but you see here there is I. So this is a real number plus I times another real number divided by a real number. It is an element of C.
Bertrand, what's your annulus? Is it between radius 1 and 2?
On 1/2. Sorry, 2 and 1/2.
2 and 1/2.
And
But then
one
C
is
goes,
in the middle.
C goes to 1 over Z, sends the outside to the inside, no?
Yes, so it sends the annulus, so somehow it reverts the annulus with respect to the circle of radius 1.
Very good.
So the transition map is the map that sends Z to 1 over Z. And it's analytic, and its inverse is analytic, so which means that I indeed have a Riemann surface. Yeah. Sorry, so it was a bad notation, but so what I mean here is that the image is an element of the complex plane. So I will define also the Riemann sphere now by other methods. So one way to define the Riemann sphere is we started from an actual manifold that exists in R3, and we give it a complex structure. We make an atlas that is an atlas of a Riemann surface over it. Another way of defining the Riemann sphere is what's called the complex projective plane, and this will be very important. Because very often in the literature, the Riemann sphere is noted as CP1. CP1 means complex projective plane. And it's defined as follows. So you start from C square and you remove the point 0, 0 in C square. You just remove the point 0, 0 in C square, and you quotient by an equivalence relation. Well, You take this space and you quotient it by the equivalence relation. And the equivalence relation is, you say that Z1 upon Z1, Z2 of C square is equivalent to lambda Z1, lambda Z2 for every lambda belongs to C star. So this is an equivalence relation. The quotient is well defined. And that's called CP1. So can we give CP1 the structure of, so can we make an atlas that is an atlas of a Riemann surface over it? And yes, the answer is we take an open set which is the set of Z1, Z2. So the equivalence classes of Z1, Z2 such that Z2 is different from 0. This is an open set of CP1. This is well defined because Z2 different from 0 goes to the quotient. It's compatible with the equivalence relation. And on it you define phi1 of Z1, Z2. So this equivalence class is just Z1 over Z2. It belongs to C. And again, this is well defined in the equivalence class. V2, same way. So it's the set of equivalence classes, sorry, Z1, Z2, such that now Z1 different from 0, and phi2 of Z1, Z2 is Z2 over Z1. That again belongs to C, and the transition map psi 1, 2 of Z equals 1 over Z. And those two counts cover the whole space. Say. And again, the transition map is the map that goes from C star to C star. Let me then define the Riemann sphere by yet another method, which is from an abstract atlas. So, well, first you can prove that those two manifolds are isomorphic. Isomorphic meaning that there is a map from the CP1 to the previously defined sphere, the Euclidean sphere. There is a map that is everywhere analytic. Whose inverse is everywhere analytic. Okay. So they are isomorphic, so basically it's the same object. I will consider another definition, which is take two disks in C. So let's call them U1, which is the disk of center 0 and radius 1. U2, which is the disk of center 0 and radius 2, R2, and such that R1, R2 is larger than 1. The product is larger than 1. So you take two disks, and I will do, as my previous construction, I will consider the space, the set of points Zi belonging to C cross the pair 1, 2, such that Z belongs to Ui. And I will quotient by the identification. So I will say that Zi is equivalent to Z prime J if and only if, well, either Z equals Z prime and I equals J, or z equals 1 over z prime, and I plus j equals 3. This is an equivalence relation. And the transition map psi of z, again, is 1 over z. And just so basically it means that I take a disk, I take another disk, so this one of radius R1, this one of radius R2, and I identify all the points that sit in the annulus of, so I take the annulus which is between radius 1 over R2 and R1, and I identify these with the annulus of radius between R2 and 1 over R1. And because of this condition R1, R2 greater than 1, this annulus is not empty. Okay. And basically I glue these together, so I glue two disks along an annulus and you get a sphere. So now what's interesting is that you can take the limit when R1 goes to infinity and R2 goes to 0. So consider the limit, let me put quotation mark, R1 goes to infinity and R2 goes to 0. So somehow U1 tends to become the whole C, whereas U2 tends to become the point, only 1 point, 0. So if you want, you have a very large disk and a very small one. And in the limit, basically, what that means is that you are going to glue the whole C to just a point. And the point, remember that the point in the second card, so if I call Z the coordinate in the first card and Z prime the coordinate in the second card, remember that Z prime equals 1 over Z. That's my transition map if I want to identify the two coordinates. So 1 over 0, if you take it back into this map, it will be infinity. So another way to define the Riemann sphere is that this is, so the Riemann sphere is what I will call, let me call it C bar, because it will be a compactification of the complex plane. So it's C union, just the point at infinity. But when you say that, you cannot recall that a compactification, you really have to explain how you glue. And this means that you have to define a vicinity, a neighborhood of this point at infinity, and say how the neighborhoods are defined. So basically you need to put a topology on that space. And define the neighborhoods of infinity. And neighborhoods of infinity in this limit were small disks. And when you bring them to these are big annulus. So a neighborhood of infinity is basically the outside of a circle. Okay. We have seen several equivalent definitions of a Riemann sphere. C bar equals CP1 equals Euclidean sphere. And so on. Okay. So it were just some definitions. Now let me give you another example of a Riemann surface. Another example of a Riemann surface, which is the torus. So I think this is section 2. The torus. So choose tau belongs to C such that its imaginary part is strictly positive. So in my complex plane, 0, 1, and I take tau somewhere here. Okay. And I will draw the lattice. I will consider the lattice z plus tau z. Z plus tau z is the set of, so it's the set of points which I get from 0 by shifting either by vector, by this vector or by this vector. Okay. Okay. And I will define C tau will be the complex plane quotiented by z plus tau z, which means that it's the set of points. So which means that 2 points z is equivalent. A point z is equivalent to another point which is of the form z plus a plus tau b. A and b integers. So which means that I identify this point with this point with this point with this point and so on. You can equip it with the structure of a Riemann surface. So you have basically to cover this with open sets. Okay. So this will cover everything. And the transition maps. The transition map from one space, from one, the transition map from one neighborhood to another will be always of the form psi of z equals z plus a plus tau b. So there are translations, and these are indeed analytic functions whose inverse is analytic. And to answer the previously asked question, two torus are not necessarily isomorphic. So, I mean, if you consider the equivalence class of atlases that you can put on this torus, it will not be equivalent to the equivalence class of atlases that you can put on another torus of different tau. So basically, the question you can ask is under what condition tau is isomorphic to tau t prime. We will answer that question much later in chapter 5. So what are the equivalence classes of tau? So what are the different complex structures that you can put on just on a topological torus? So maybe it's a good time to take a small break. So the next part of the lecture will be to define. So now we will come back. We will come to our main purpose, which is define a Riemann surface from an algebraic equation P of x y equals 0. This is a polynomial. So this will be the topic of the next hour.
I can do the blow. Go.
So I start again. So now we want to re-enter the realm of algebraic geometry and define a surface from an algebraic equation. So the general idea is that an algebraic equation will define a compact Riemann surface. And the converse is also true. Every compact Riemann surface can be represented by an algebraic equation. But there will be some subtleties. So let me start with an example. And my example will be the one, basically the nearly only one, for which there is no subtlety. So take the equation y squared equals x squared minus 4. So it's a very simple degree 2 polynomial. And define the surface sigma tilde. Sorry, define sigma tilde will be the set of x, y, such that y squared equals square root of equals x squared minus 4. It's included in C cross C. It's a tilde. So it's a subset of C cross C. Is it a manifold? Is it a surface? Well, first, you realize that C cross C is a 4-dimensional space. And here you have one equation, but this is a complex equation, so it really means two real equations. So it means the real part have to be equal and the imaginary part have to be equal, so you have two real equations. So this is a codimension 2 subset of R4. So locally it will look like something two-dimensional. It will look like a surface. Can we make it a Riemann surface? Can we find some set of charts, neighborhoods with transition maps and so on? And so I will define the following. Well, so if you are able to plot it in R4, which is really difficult, it would look like something like this. Okay. Also, another remark, R4 or C cross C is not compact. And here you can really go to x and y going to infinity, so it will not be something compact. So sigma tilde is not compact. So let me define the charts. So I was saying charts, but apparently charts. So I will define 6 charts to cover that surface. So let me define V plus. It is the space of pairs x on square root of x squared minus 4. X belongs to what I would call U plus, which is just the complex plane where I remove the segment minus 2, 2. So my U plus will be just the complex plane where I removed the segment minus 2, 2. Okay. So it's included in sigma tilde. It's an open subset of sigma tilde. V minus will be x minus square root of x squared minus 4. By definition here, the square root is the square root that sends positive numbers to positive numbers, and that has the cut on the negative real axis. My square root is the standard square root. X belongs to U minus, which is another which is again the same thing. So U minus is the same thing. Then I will define V plus minus will be the set x I square root of 4 minus x squared, such that x belongs to minus 3 half 3 half cross minus 1 half. So V plus minus, or U plus minus, will be in the complex plane. It will be this rectangle. It's this rectangle. And V minus plus is more or less the same thing, except I change the sign of the square root. So it belongs to So it's the same thing. And then I will define V1 is the space of 2 plus z square z square root of 4 plus z square So U1 is just a disk, and U minus 1 is just a disk. Okay. So here this is it. So here it's the exterior, and here is the exterior. So if you look at what all those labels are on my sigma tilde, somehow there is here two special points. This point is the point minus 2, 0, and this point is the point 2, 0. Okay, and somehow U plus is everything above this circle, V minus is everything below that circle. Sorry, I mean V plus is everything above, V minus is everything below. V plus minus is something that sits there. V minus plus is something that sits there. And V1 is a circle. So somehow it surrounds that point. So it's a circle glued like that, and a circle glued like that. And you can check that every point is covered by one of my charts. Every point of sigma tilde is in one of the charts. And the transition maps, so you have, oh sorry, and I forgot to say what are the phi's. Phi plus over x equals x, phi minus of x equals x. These are easy. Phi plus minus of x equals x, phi minus plus of x equals x. And here phi 1 of xy equals square root of x minus 2, and phi minus 1 of xy equals square root of x plus 2. So every point of sigma tilde is covered by one of the charts. Many transition functions. So first observe that V plus, V minus don't intersect, and also V1 and V minus 1 do not intersect. All the others do intersect.
Sorry. So from your picture, it looks like we could have just two charts if we had the charts V plus and V minus to be a bit bigger and overlap. So
no, this is not possible because it would not be homeomorphism. It would not be bijective. It's 2 points. 2 points in. The same point in U plus. Sorry. No, it cannot overlap. It's an open. It's a subset of the complex plane. It cannot have somehow 2 points over 1. It's really a subset of C. There is no notion of overlapping. No. So, well, the idea is that you can check that every transition maps are analytic, and some transition maps. So most of the transition maps, for instance, the transition maps from V plus to V plus minus. From U plus psi. The transition map that goes from, let's say, U plus to U plus minus is just the identity. So many of my transition maps are simply identity. So basically it means that if you want to identify this point with this point, you just take identity in the complex plane. It's more subtle when you look to the transition maps from, let's say, U1 to U plus. So U1, so V1 will overlap V plus in a certain region around point 2. And U1, basically one half of the disk, will do one circle like that. And the other half of the disk, let me choose another color. The other half of the disk will overlap, in fact, U minus. Okay, and the transition map, well, it's written here. So the transition map from U plus to, let me write U1 to U plus is simply Z goes to 2 plus Z square. Okay, the inverse map is X goes to square root of X minus 2. And within that green region, avoiding the point, this is analytic and bijectively analytic. Okay, so this makes an atlas of a Riemann surface. All those charts make an atlas of a Riemann surface. All the transition maps are analytic, and their inverse is analytic, so it makes a Riemann surface. But there is one point which is that it's not compact. The reason? Well, we have a finite number of charts. We have 6 charts, but 2 of the charts cannot be put in a ball. 2 of the charts cannot be put in the ball of C. I mean, they go to infinity. These 2 charts go to infinity. So there is a way to add some new points to my sigma tilde to make it a compact Riemann surface. Somehow I will add 2 new points that I will call plus infinity infinity and minus infinity infinity. That's the name I give to these 2 new points. So I want to define 2 new points, and I will need to define 2 charts that are the neighborhood of those new points. It's very similar to how we compactified C to get the Riemann sphere. And somehow here I will compactify the large region of V plus in the same way we compactified C to get the Riemann sphere. So let me call V plus infinity, which would be the space of X square root of X squared minus 4, such that let's say modulus of X is larger than 4, and union the point which I will call this point plus infinity infinity. So this is a new point I add.
4 or 2?
Excuse me?
The limit 4 or 2?
4. I want to be really far from the cut. 4 is enough. I could choose 5 if you like. Doesn't matter. Okay. And I will send it to, and I will take the transition map phi plus infinity of xy, will just be 1 over x. So which means that d plus infinity will be a certain domain, domain around 0 in the complex plane. Okay, sorry. I define that for those points, and phi plus infinity of the point plus infinity infinity will be 0. Okay, so my new point. So the image of all those points are sent to everything but 0 here. And the image of that point is 0, and okay, that's my new chart. And now if I take my sigma, if I define sigma, which is my sigma tilde union those 2 points, plus infinity infinity, and minus infinity infinity, this is a compact Riemann surface. And now let me show you that it's isomorphic to the Riemann sphere. So it was a very complicated way of defining the Riemann sphere. So there is a map. There is a map from sigma to my C bar, which is you send the point xy. Sorry, let me do it the other way around. There is a map C bar to my sigma, where you send the point z here to the pair z plus 1 over z, z minus 1 over z. And it's invertible, it's analytic everywhere, and you can check that. And it's on sigma simply because z plus z minus 1 over z to the square, so which is the y, equals z plus 1 over z to the square minus 4. Simply based on that equality. So, which is just y square equals x square minus 4. So this is a bijection. It is bijective. And analytic in each part. And the inverse is also, so this f, and f, so f is on f minus 1 also. Which means that the two Riemann surfaces are isomorphic. So in the end, when I add those 2 points at infinity, what you get is the Riemann sphere. Let me go now to more general. Let me go to general algebraic equations.
Excuse me.
So
let's suppose you have a very strange surface with a number of directions, like non-complex directions. Is it always possible to add
yes,
this number
yes.
of points to have the
Yes.
Riemann sphere?
Yes, and that's more or less what I'm going to do. So now start from P of xy equals 0 equals sum of Pij, xi, yj. So first of all, well, on say that the degree in y of p is, let me call it d. So locally, there are d solutions y1 of x, yd of x. That system. So if you want to solve this equation for y as a function of x, you find generically d solutions because it's an equation of degree d. Okay. And the idea is how are we going to glue them together to make a Riemann surface. So we want to do as before, remove some cuts and take neighborhoods of the extremities of the cuts, the branch points, neighborhoods of the edges of the cuts, and so on. And how do we do that? First, we have to identify the branch points. And the branch points are, so let's consider the set. Let's consider the set of points x, y, such that p of x, y equals 0. So let me start by defining sigma tilde equals the set of x, y, such that p of x, y equals 0. It's a subset of C cross C. It's a subset of C cross C, but first it will not be compact and it will not necessarily be a manifold, Riemann surface. I will explain why. But then define the object sigma tilde thing will be the set of points such that xy, such that p of xy equals 0 and the derivative with respect to y of xy equals 0. So it's a discrete subset, so it's a finite subset. Of sigma tilde. So it's the equivalent of those 2 points. And now let me call x thing be the set of all x such that there exists xy belonging to sigma tilde thing. So basically it's the x projection of all the singular points. So somehow you have a complex plane, C, and in that plane you have a certain number of points that is x thing. That are those points. Now choose a graph, a tree in fact, connecting whose vertices are x. So let's choose something like that. Anything that cuts the plane. And choose. So now we shall make cards. UI will be C minus gamma. Choose a tree, let's call it gamma. So that's my graph. Gamma is a graph. Okay, and take UI with I equals 1 to D. That are those copies. If you take a point, fix a given point in UI. Okay, let's call it x0. And there are D solutions, so there are D. So let's call y1 of x0, yd of x0 solutions of p of x0, y I of x0 equals 0. Okay, so above that point, I label the solutions. They are all distinct. They are all distinct. They are all distinct solutions because I'm not at one of the singular points. And the idea is that since now the complement of gamma is sorry, let me also go to infinity on 1 point at infinity in CP1. So now the complement, sorry, what did I want to say? The complement is topologically a disk. So this is a topological disk. So this is, so in fact it's CP1, so it's a disk. So since it's simply connected, it means that there is a unique way to analytically extend all the yi to the whole ui. So it means yi of x can be extended on ui. So now if you take vi, the set of point x, yi of x, for x belongs to ui, this is included in sigma tilde. This is the equivalent of what I called v plus and v minus that were outside of my segment before. V plus and v minus. V plus and v minus. That was the upper part of that surface and the lower part of that surface, but now I have more of them with I equals 1. Now I need to also define some charts that will cover the edges. Okay, that's quite easy to do. You shall take uij equals 1. Okay. Well, I'm not going to do it in full details, but the idea is exactly the same thing I did with square root of with y squared equals x squared minus 4. You define some charts here, and you want to glue two solutions when you cross the edge, and you have to figure out what solutions you glue, but you glue them, and the transition map is simply identity. You glue x with x. Basically, you glue the point x, y, I to the point x, y, j on each side of the two rectangles. Okay, so I'm not going to do it in full details. What is more subtle is what happens near those points. And near those points, generically, so if you have a generic branch point, it will behave like a square root, and it will be exactly the same as I did before. So in the vicinity of, I assume, the least singular possible. So remember that we assumed that p prime y of AB was 0, but the least singular possible means that I assume that the x derivative is non-zero and the y second derivative is not 0. Let me assume that. And you can choose neighborhood one. Okay, a local coordinate. So you should choose UAB. Will be a small disk, d of 0 and some radius r, with r positive. And the transition map will be so I will define it the other way around. 5 minus 1 AB of z will be a plus z square and on y of a plus z square okay, the one such that y of a equals b. Okay, it's just exactly what I did before. That's not the most interesting thing I want to do. Also, the points at infinity, you can compactify them. It's the question you ask. There are different kinds of points at infinity that you can compactify. There are the most regular ones that you compactify exactly like CP1 as I did before. And there are some points at infinity that can also be branch points somehow. And you have to be more careful. I'm not going to do it in full details, but what I want to say is that there is a way to there is a way to define transition maps and all that near all kinds of singular points. But there is one type of singular point I want to insist on. And what kind of singular points is the kind of singular points that can arise when that's called nodal points. Nodal points are points where they are points where AB, so P of AB equals 0, P prime Y of AB equals 0, so they are singular points, but they are such also that the x derivative vanish. What happens in that case when you have both the y and x derivative vanishing? It means that, in fact, there is no normal vector to that point on sigma t. The normal vector is vanishing. And in fact, what it looks like is just a crossing. So here you have the normal vector, here you have the normal vector, here you have the normal vector. Remember that the normal vector has coordinates p prime x, p prime y. So at that point, the normal vector vanishes. In fact, it's because there are two normal vectors at that point that are the eigenvalues of the second derivative matrix. Let's assume that the determinant of the second derivative let me assume that it's not degenerate. Okay. So that will give the less singular kind of nodal points, but you can also have more singular nodal points. But let's assume that. So a typical example of this situation is the equation y squared minus x squared equals 0. Which is just the same thing as y minus x times y plus x equals 0, so it will look like that. So this point, what happens in the vicinity of this point AB? Well, first, it's easy to see that if you take sigma tilde and you intersect it with a certain ball of center AB and some radius r, so it's a ball of ball in C square. This is not homeomorphic to a Euclidean open set. So basically, it does not look like a Euclidean set. It looks like, but in fact, now if you take sigma tilde star means I remove the center. I remove the point AB. Then this is the union of two disks, two Euclideans. So basically, it's a small disk where I remove the center, union, another small disk where I remove the center. Remember that what I plot as a line here is in fact locally somehow it's the complex plane, and this one also is locally the complex plane, but they cross at only one point. This picture is misleading because it looks like a three-dimensional representation, but we are really in four dimensions. In four dimensions, there is only one intersection point. So it's like you have two disks, and somehow the point AB belongs to the two disks. So there is one way to desingularize sigma tilde. So how do you desingularize sigma tilde to make it a Riemann surface? You remove, so you take sigma tilde, you remove the point AB, and you add to it two new points, one which I will call plus AB, or let me call it AB index plus, and AB index minus. So somehow I have removed the point which is there. So I have some neighborhoods here. So I remove that point. When I remove that point, I have two disks. And now I add two new points, but I do one to the first disk and one to the second disk. So somehow I do as if they were two different points. Are you okay? So sigma will be that. And I have to define the neighborhoods of those points. So I define the neighborhoods of those points. So the neighborhood of that point is one of the two punctured disks, and the neighborhood of that point is the other punctured disk. There is easily a map. There is a map from sigma to sigma tilde, which is that for every xy, I send it to xy, but for AB plus, I send it to AB, and AB minus is also sent to AB. So this is for xy different from AB. And do that. So there is a very simple map from sigma tilde, from sigma to sigma tilde. And the idea is so by this procedure, we can get with the map which is analytic. But there is no inverse map in general, except for example, the examples I showed before, y squared equals x squared minus 4. In that case, there was an inverse map, which was analytic. But in general, there is not necessarily because of another case. So what I try to show is that when you have an algebraic equation P of xy equals 0, you get a compact Riemann surface with an embedding, with an immersion in. So instead of C cross C, in fact, let me say CP1 cross CP1. It equals to infinity. So somehow we have an abstract Riemann surface, and we send it in C cross C. So instead of plotting C cross C, well, let me plot R cross R. If you would really like to plot it in C cross C, then this would be a two-dimensional. I mean, you would need to do the picture in 4 dimensions, but I'm not able to do it on paper. But so it looks like that. So this picture, what does it mean? It means that for every point P on your Riemann surface, there is 2 maps. One which is y of P, and one other one which is x of P, which are complex numbers. And at the intersection, you get this point. This point is the point x of P, y of P. There is another way to deal with the compactness at infinity, which is instead of doing an embedding into C cross C, you can directly do an embedding, an immersion into CP2. So let me define projective curves. Okay. So now let me recall that CP2 is the set of points Z1, Z2, Z3 that belongs to C cube minus the point 0, 0, 0. And quotiented by the equivalence relation Z1, Z2, Z3. It is equivalent to lambda Z1, lambda Z2, lambda Z3, for lambda belongs to C star. Okay. Now take P homogeneous polynomial in C of Z1, Z2, Z3. So a polynomial with 3 variables, so that you can write P of Z1, Z2, Z3 equals sum of I, J, K, Pi, J, K, Z1 to the I, Z2 to the J, Z3, to the K, but with the condition that I plus J plus K is D. Okay. So it is a homogeneous polynomial, and so now the set, the equivalence classes of Z1, Z2, Z3 such that P of Z1, Z2, Z3 so let me call that sigma tilde. It's included in CP2. So it's a subset of CP2. Since the polynomial is homogeneous, this is well defined in the quotient. This depends only on the equivalent classes. So now the advantage is that CP2 is already compact. So you are sure that you will get something compact. But again, you have the problem of nodal points, which means that locally it can be non-Euclidean. So you still have to desingularize it. So you can always also, so I said that you can embed the curve in CP1 cross CP1, but you can also, you can immerse it in CP1 cross CP1, but you can also immerse it in CP2. Just remark one thing, that if you are, if you take account Z3 different from 0, in fact, Z1, Z2, Z3 is equivalent to Z1, Z2, 1. So basically you can replace Z3 by 1, and instead of a polynomial of 3 variables, it's equivalent to consider a polynomial of 2 variables.
Sorry, why not Z1 over Z3, Z2 over Z3?
Sorry, yes, you're right, sorry. on call that x, on call that y. So, I mean, you are back to a polynomial of c of x1. So basically you have the sum of pij d minus I minus j xi yj. So I just need the same thing as before. There is a theorem which is that in some way algebraic equals compact. With quotation marks. So here I have shown you that every algebraic curve can be immersed, can be realized by this desingularization procedure. From every algebraic curve you can get a compact Riemann surface. But vice versa, you can prove that if you have a Riemann compact surface, it can always be realized in this way as an immersion of polynomial equation. So the true statement is that every compact Riemann surface sigma can be realized, can be immersed in CP2 with at most simple nodal points. So the difference between immersion and embedding is truly a bijection, and immersion can have those points, so it's not necessarily bijective, so it means that you remember in the map from sigma to sigma tilde, it was not bijective because two different points of sigma can be sent to the same point of sigma tilde. In an embedding, this would not be the case. So basically, it's not always possible to find an embedding in CP2. It's not always possible, but you can always choose a way to. You can always choose your polynomial such that the worst thing that can happen is simple nodal points. That means p prime y and p prime x vanish, but the second derivative matrix does not vanish. Okay. But this can be also said that every can be now embedded. Sorry, algebraically. And also here in CP3. If you allow CP3, you can avoid every kind of singularity. So you can always find a polynomial such that there is no nodal point or no singular points. So the idea behind that is that, it's the notion of algebraic topology. Somehow, compactness is equivalent to algebraic. Algebraic is equivalent to compact. This is strange, but so now let me start with the next chapter. So I will continue for just a few minutes, just introduce the beginning of the next chapter. So chapter 2. So this is chapter 2. Yes, which is functions on forms on Riemann surfaces. And definition. So if you want to, so what is the definition of a meromorphic or holomorphic function. So meromorphic. So let me say holomorphic. And sigma. It will be the collection of holomorphic as meromorphic functions in each chart. Fu in each fui in each ui. Now it will be holomorphic in the sense of, or meromorphic in the sense of function defined on an open set of C. Remember that UI is an open set of C. And such that they are compatible with transition functions. So Fuj equals Fui composed with psi ji. Psi goes from uj ui. That's how I define it. So basically, if you start in uj, so if you have, remember that it comes from vi vj, and if they have an intersection, so this is ui, uj. Remember that here you have the map psi ui uj, and the inverse map is psi uj ui. And basically you want f to take the same value wherever, so if you are at a point here, so it's there and there, you want it basically to have the same value. So this means that f of p is f of fui of phi ui of p is independent of choice of chart. There is an easy theorem, is that if you have a meromorphic function and if the surface is compact, there is at most a finite number of poles. And also, the total number of poles can be only finite. And the reason is, if it would be infinite, there would be a converging subsequence, and the point of convergence would not be, it would be an essential singularity. The function could not be meromorphic at an infinite accumulation of poles.
Excuse me, could you repeat, please?
Okay, but I will say that again later, but I'm just saying that the total number of poles of a meromorphic function is finite. And the reason is that if it would be infinite, you could find a convergent subsequence, and the point where it converges, basically it would be an accumulation of poles and in an open set of the complex plane, and there is no isomorphic function that has an accumulation of poles in the complex plane. So, okay, I will just define now differential forms. So, forms, one forms, along or meromorphic, the definition. So again, it's a collection FUI follow in UI, and such that f uj of x equals f ui of psi uj ui of x times d psi uj ui of x over dx. So which means that now f of p equals f ui of phi so basically what I'm going to write is that p belongs to sigma on phi ui phi vi of p equals x belongs to ui. I'm going to define f of p will be f ui of x times dx is independent of the count. So when I multiply by dx, I get something independent of the count. So this is locally a one form on C. There is the same thing with kth order form. So it's not really a k form, but so this was for one forms. But let me replace this definition with kth order forms. Kth order form is the same thing, but you will put a power k here and the power k here. So in particular, k equals 0 are functions, k equals 1 are forms, also one forms, k equals 2 equals quadratic form, quadratic differential, and in fact, you can also consider the case where k belongs to z over 2. So half integers. It's what's called spinors. For spinors, it's not totally true that this is defined independent of the count. It's just up to a sign. So it's well defined, so it's defined independently of the count up to a sign. I will not talk much about spinors, but they will happen when we consider bundles and all that. So I will stop here. Next time we will study what are the properties, or general properties of forms, of functions, and a complete classification of all possible forms on functions, the basis of all possible forms on functions on the Riemann surface, and especially starting from the equation p of xy equals sum of pij xi, yj. What are all the functions on forms that are defined on such an algebraic equation? And it will strongly involve what's called the Newton's polytope. So in the plane ij, you plot a point whenever there is a pij. Okay, that's a set of points in z cross z. That's a set of points in z cross z, and just by combinatorics of this set of points, we shall be able to classify all possible functions on forms, and it's very beautiful because it's more combinatorial. And it's called the Newton's polygon method. So just by the combinatorics of this set of points and some very easy things, we shall be able to find all forms on functions. Okay, thanks.
Other questions?
Do you have example or counter example when the second derivative, what happens when the second derivative vanishes?
You mean the determinant?
Are you factorizable?
Well, many situations can occur. Yes, we can discuss that.
So when you have polynomial of 3 variables, then the surface defines something like complex, like not a curve but a plane, or complex plane, or complex curve.
Okay, you mean not homogeneous, you mean really three-dimensional object.
Because in 2 dimensions you just have something like.
Yes, you can define you can define other kinds of algebraic manifolds, but I'm concentrating on algebraic surfaces, so manifolds of dimension 2. That's what my lecture is about. But there are lots of interesting things with algebraic manifolds.
When you consider a function of 3 variables, all of them are complex?
Yes, but here it was homogeneous, and in fact it depended only on the ratio, so there were only 2 independent ones.
It's homogeneous.
Yes.
No more questions? Okay, thank you again.